if you are. So welcome everybody to the third day of the conference. We're very happy to have Tomoyuki Arakawa joining us. And he's going to tell us about R-filtration and Vogan filtration.
Thank you very much, and thank you very much so much for the invitation to give a talk here. And so I'd like to talk about ongoing work with Anne Moreau. So the subject of my talk is the 4D, 2D duality discovered by Beem, Lemos, Liendo, Rastelli, and Van Rees quite recently. And so this gives us a map from the category of four-dimensional N equals to 2 super conformal field theories to the category of vertex operator algebras. And so it's defined in such a way that the Schur index of the four-dimensional theory, which is the Q series, is exactly the character, the normalized character of the corresponding VOA. So this is a trace of V Q to L0 minus C over 24. Right, so this map has several properties. So first, for the central charge of the VOA is minus 12 of central charge of four-dimensional theory. So this means that the VOA coming from 4D is never unitary. So if you start with the unitary theory, you end up with non-unitary theory. So in particular, so this map is not surjective. On the other hand, so correct me if I'm wrong. And so this map is defined by certain dimensional reduction. So it's natural to think that it loses a lot of information, but in fact, this map is expected to be injective. So this means, in other words, the VOA is a complete invariant of the corresponding for this theory. So this is a very good news for us, because this means that the inside the category of a vertex operator algebra, we have a very, so because this, for this theory is extremely rich, and if this map is injective, then we have a very interesting family of vertex algebra as full subcategory of the category of vertex algebra. And so now I want to remind you about the associated variety, concept of associated variety, and the conjecture of Beem and Rastelli. So let V vertex operator algebras. So by state field correspondence, we can identify this vector space with the span of the normal ordered product of a field, the descendant of a field, where this field generating a field of the vertex algebra. And one nice thing about the vertex operator algebra is that the any, so this is a result of Haishan and Lee. He showed that any vertex operator algebra is canonically filtered. This is obviously not true for any algebra, but for vertex operator algebra, it's always filtered. So how we define filtration? So we can define a decreasing filtration by counting the number of derivation here. So we can define FPV to be span of this element such that the sum of this Ni is equal or greater than P. So this obviously defines a decreasing filtration. So if 0V is this because there's no relation. And so you have this kind of filtration. And so intersection is 0. So this means corresponding associated gradient is isomorphic to V as a vector space. And in fact, this has a natural structure of a Poisson vertex algebra. And this Poisson vertex algebra, if we restrict this Poisson vertex algebra structure to this sub space, so this is obviously subspace of GUR of V. And in fact, one can see that this is a subalgebra, commutative subalgebra. And in fact, this has a structure of Poisson algebra. And the Poisson structure is easily described. So the multiplication is the normally ordered product. And the Poisson bracket is you look at the first term of the OPE, in the OPE. And it's easy to check that this gives this a quotient, sub-quotient of V, a structure of Poisson algebra. And this is called a Zudd-Sitz algebra. So because it's and this is finitely generated. It's generated by the image of these generating fields. So because we have a commutative ring, we can define, it's natural to define the corresponding spectrum, and it's called the associated variety of. So this is a Poisson, a fine Poisson variety. And a conjecture of Beem and Rastelli says that the Higgs branch of the 4D theory is this associated variety of the image of the 4D 2D correspondence. So this is for any 4D n equals to 2 superconformal fields. So this is very surprising because VOA is purely algebraic object, and Higgs branch is a geometric object. But if you believe that this map is injective, it's natural that we can recover everything from the corresponding vertex algebra. So this is somehow evidence that the 4D 2D duality gives a complete invariant. And this conjecture is known to be true for a theory of classes. And so in this case, Higgs branch are varieties called Moore-Tachikawa varieties. And but there is a certain subtlety in this statement, which is the following. So this algebra is not reduced. So there are nilpotent elements, while the Higgs branch chiral ring is reduced. So the statement is rather this is isomorphic to the reduced part, a reduced scheme of the associated variety. So in other words, so this Higgs branch chiral ring is isomorphic to the reduction of this Poisson algebra. And to remedy this, Beem and Rastelli introduced a refinement of the canonical filtration defined by Lee, which goes as follows. So we have a vertex operator algebra coming from a four-dimensional theory. And so 4D theory has several charges. And so it has a grading by conformal weight. So this is again value of L0. And also half integer called R charge. And so these are half integers. And so this R charge is equals smaller than conformal weight. So you can define filtration in the following manner. So you look at the subspace spanned by vectors which have R charge that has equal or smaller than this number. Then you get filtration, again a decreasing filtration. And it's separated. And such that so the statement is that the associated graded. So this time I write as gur R of V. So this is again a Poisson vertex algebra. And each term contains Fp of V. So this means there exists a Poisson vertex algebra homomorphism from associated graded with respect to least filtration to the associated graded with respect to this R filtration. And so this restricts to a surjective map from this Poisson algebra to this quotient. Sorry. And the statement is the kernel of this map is exactly the nil radical of RV. So in other words, the image of, so this is a surjection. So the image is exactly the Higgs branch, chiral ring of 4D theory. So this is nice, but the problem for me is that to define filtration, we need it comes from 4D theory. So after sending 4D theory to the 2D theory, we cannot see the R charge without knowledge of the corresponding 4D theory. And so it's a problem for us because 4D theory is not something mathematically defined. But if you believe that the VOA is a complete invariant of a 4D theory, we should be able to recover this filtration. So the question I want to ask is how to reproduce this R-filtration from vertex operator algebra. And so this is the question I want to ask, and so on. And so let me explain how I think of this. So we have the associated variety of maybe spec of those algebra, and I consider its smooth part of this associated scheme, which is open subset, and I make some assumption which is true for genus 0 class is a chiral algebra. So first, I assume that the VOA is simple. The second, U is symplectic. So meaning that so XV is a Poisson scheme, so you can restrict Poisson structure to this U, and so this gives you a structure of smooth symplectic variety, and the complement of U has a codimension at least 2 in XV, and this condition means that a global section of this smooth symplectic variety is exactly the RV. So this means okay. So this is what this means, and so because this is a closed subset, it's defined by some ideal. So I take some defining. So let's I be the defining ideal of this closed set, where Fy is some element of Rv. And then I take a lifting of this element to V. So this means AI is Fy modulo F1 V. And then I can define new filtration as follows. I define gamma P of V to be elements in V such that if we multiply field corresponding to these elements sufficiently enough, then it belongs to Fp of V for sufficiently large. And then this obviously, so this it's easy to see that this this space contains FPV, but in general, this is larger than FP of V. And so this defines decreasing filtration. Oh, sorry, of V. And then one can show that the intersection of this filtration is 0 if V is simple. So that its associate, the corresponding associate gradient is the isomorphic to V as a vector space. And also the corresponding associate gradient is it has a structure of Poisson vertex algebra. So this means we have so because of this inclusion, we have a Poisson vertex algebra homomorphism from associate graded defined by the filtration to this filtration, associate graded associate with this filtration, and which induces surjection from RV to this quotient. And the last statement is that this is a reduced, is the reduction of RV. So the kernel consists of kernel is exactly the nil radical of RV. So our conjecture.
Can I interrupt? Just checking. So can you go up just a little bit?
Yeah.
So just the definition of gamma p. What means?
Yes.
What is n? What does mean n much greater than 0?
So we apply field some elements from here. And so if we apply this field sufficiently enough, then it belongs to FPV. So this means the number of this element is if number.
I mean, because it contains FP when n is equal to 0, right?
Right. So FP, element of FPV satisfies this condition. So I didn't really explain, but this was proved by Haishan Li. So if you take element of V, so this is obvious from the definition. So if you take element of FPV, then if we apply this element, it still belongs to FPV because FPV is defined by the number of derivatives. If this one has already P derivatives, this already have P derivatives. However, if V does not have derivatives less than P, it may happen that if you apply this element, it can return as a sum of elements which have derivatives more than P. That's the definition.
Yeah, okay, but I'm not sure I understand why there's a conditional n here. Any n will do that.
So one thing that
It's supposed to correspond to this R filtration that you had before.
Yes, yes.
And the intuition that this is going to be that the quotient is nilpotent.
Sorry, I cannot hear you.
The intuition that the quotient there is that the kernel is nilpotent. What is that?
Sorry, I cannot really hear.
Is the kernel going to be the real radical?
Kernel is the linear algebra. That's my statement. So the kernel of this map. Kernel of this map is so I'll explain an example. Maybe we can discuss after that.
Okay, thank you.
So the conjecture is that this coincides with the R-filtration. So this means so gamma P of V is an element which have over this form. And so this kind of filtration is modeled by a filtration defined by Vogan in 90 in the paper associated variety and unipotent representation. This is a direct analog, direct generalization of the filtration used by Vogan. So he used this filtration to show the reducibility of associated variety of the primitive idea of UG. So we call this Vogan. And so maybe I should explain example. So let me explain the simplest example, which is Birazoro opaque minimal model. Then the Zucit algebra is of this form. So X is image of stress tensor. And N is, I think, P minus 1 times Q minus 1 over 2. So this is already so this is a fat point. So the reduced scheme is just a point. And the open set U depends on this number N. And so this coincides with the whole thing if N is already a 1. So in this case, RV just C. And it's empty set if N is greater than 1. So there's no regular points. And for N equals to 1, so this filtration, because there's no N is empty set, complement is an empty set, the filtration is the same as original Lee's filtration. But so this is okay because RV is already C. So this is so this means already. So this is the same, but this is already C. So this is already reduced. So there's nothing to do here. But if n is greater than 1, then this ideal is generated by X. And then you find that this stress tensor belongs to gamma 1 of V because power of n is 0 in RV, and this is the same as yeah, so this means how to explain. Yeah, so if you apply Tz to n, so apply Tz to Tz to n minus 1. So this belongs to gamma 1V. So this means that the TTT is element of gamma, F1V. So this means that the T belongs to gamma 1V. So this implies that the V over R1 V is C. So the kernel is exactly the new radical. Does this clarify your question?
Well, my question was probably minor because it was just about the n. Sure, yeah, thank you.
So maybe this is all what I wanted to say a bit earlier, but I stop here.
So thank you so much. Are there any questions? From Zoom?
Sorry, I cannot hear you.
We can't hear you, Matthias.
Maybe the headphones?
Can you hear me now?
Yes, that's perfect.
Okay, good. Yeah, a very nice talk. So I was wondering, can you actually reconstruct this R charge now from your construction? I mean, in some sense, you avoided introducing the R charge by defining this filtration differently, but is there a way of sort of now reconstructing it from your construction?
Yes. In principle, it's possible, but in practice, it's quite difficult because we need to know the so we have map from GUR of V to GUR of gamma V. So this is a module of this. And another conjecture of us is the so this is finitely generated GUR V module, and if we can describe the module structure, we can reconstruct this R charge, but this is in general hard problem.
But can one describe it in terms of, I mean, is some sort of simple idea roughly right that one can describe it in terms of how many times you have to apply one of these A fields? Is that
right? Yes, exactly. Yeah.
Thanks. So basically, each of these A fields carries some non-trivial R charge, and each time you apply it, you increase the R charge?
Yeah, that's correct, yeah.
But I guess this won't completely determine the R charge on the four-dimensional theory, right? Because much of it was acyclic when you made this deformation.
Right, yeah.
Other questions?
Where is the R charge valued? Is it an integer? Is it
It's a half integer.
and unrelatedly,
Sorry, cannot hear you.
these filtrations that give you a Poisson vertex algebra, like how generally does that happen? It seems like a lot of your filtrations are doing.
Sorry, okay. Difficult to hear.
Your filtrations, the associated gradient is often a Poisson vertex algebra. How general a phenomenon is that?
So it's in general true that this is a Poisson vertex. So we don't really need the assumption we made for this statement. So this is in general true. Is that your question?
Yes.
Other questions? So if not, let's thank Tomoyuki again for a very nice talk. And we'll resume.